Welcome to this explainer. Today, we're tackling a classic and honestly totally fascinating challenge in system design. We're building a high-performance URL shortener. You know, a service like TinyURL. Now, on the surface, this seems incredibly basic, right? But as you'll see, the real trick isn't just making it work. The real trick is figuring out how to scale it up to handle massive global traffic without creating a single point of failure. By the end of this explainer, you're going to see exactly how engineers take a super simple idea and literally bulletproof it for the real world. Let's get into it.
Okay, let's dive into this. Picture this. You're sitting in the hot seat of a system design interview, and the interviewer hits you with this prompt. Design TinyURL. Sounds like a piece of cake, doesn't it? You take a long URL, you spit out a short one. And when somebody clicks that short link, you redirect them to the original site. Easy. Well, it is easy until millions of users are trying to do it at the exact same second across dozens of servers. Suddenly, you have to guarantee absolutely zero collisions and zero downtime. Not so easy anymore.
Section 1. The TinyURL Design Challenge. Let's quickly lock down our core functional requirements. To really grasp the scale of those requirements, let's do a little back-of-the-envelope math. 100 million. Let's say our system needs to generate 100 million brand new URLs every single month. If you break that down, it averages out to about 40 writes per second. Okay, 40 writes per second, that really doesn't sound too bad. But here's the catch. A URL shortener is a heavily read-biased system. The read-to-write ratio is usually around 100 to 1. So for every 40 writes, we're getting slammed with a staggering 4,000 reads per second on average. And you can easily double or triple that number during traffic spikes. Now, I want you to contrast that 4,000 reads per second with this number, 3 terabytes. If we keep these links active for, say, 5 years, and assume each record takes up about 500 bytes for the URL and some basic metadata, we're going to need roughly 3 terabytes of total storage. Now, 3 terabytes isn't some unimaginably huge amount of data in isolation, but combining that storage footprint with 4,000 continuous reads per second means one very clear thing for us. A single, lonely database server, yeah, it simply will not survive. We absolutely have to scale horizontally. Let's move to Section 2 and see how this builds. The naive database solution.
The most straightforward, no-brainer way to generate a unique shortcode is to use a naive ID generation approach. Basically, every time a new long URL comes in, the database simply hands out an auto-incrementing number, 1, 2, 3, and so on. But, we don't want our short links to just be raw numbers. That looks messy. So we convert that base 10 number into base 62, which uses lowercase letters, uppercase letters, and numbers. To put that into perspective, a database ID like 104,857,601 cleanly converts into the neat little 6-character code 1LY7VK. Pretty elegant.
What's great is that this allows us to keep our data model incredibly simple. We really just need 3 things: an ID, the shortcode, and the original long URL. There are no complex joins or messy transactions happening here. The whole shebang boils down to just one main query, which is looking up a row by its shortcode. Because our access pattern is basically just a simple key-value lookup, this approach works perfectly on a well-indexed Postgres database. Or, if we know we need to shard heavily later, a NoSQL store like Cassandra or DynamoDB. Now, what's really interesting here is this fascinating trade-off, where a tiny little HTTP detail can drastically change our entire system's performance. When someone clicks our short link, we send back a redirect status code, right? Well, if we send a 301 moved permanently, the user's browser and network CDNs will actually cache that redirect. This saves our servers a massive amount of load. But the downside? We completely lose the ability to track analytics for every single click. On the flip side, a 302 found tells the browser, hey, don't cache this, so every single click hits our server. This is amazing for logging analytics, but absolutely terrible for our server load. As you can see, system design is all about these kinds of trade-offs.
Which brings us to Section 3. When scale breaks everything.
I want you to ask yourself this question. What happens at 40 writes per second when you are forced to expand across multiple regions and shard your databases? Well, the exact moment we split our database to handle the load, our perfectly logical, naive architecture, it begins to crack and crumble right before our eyes. Let's look at exactly where the system cracks. First up, our database's auto-incrementing counter suddenly becomes a massive single point of contention. Every single write has to wait in line. Second, and honestly much more dangerously, if we shard our database to fix that bottleneck, the whole auto-increment thing completely fails us. Think about it.
Shard A will generate row 500, and shard B will independently generate its own row 500. Boom, we get overlapping, colliding IDs. And finally, we start seeing race conditions where two near-simultaneous requests fight for the exact same counter value. The naive approach just literally cannot handle a distributed environment.
So clearly, we need a fix. The first logical attempt most engineers make here is to just try and bypass the shared counter entirely. They think, instead of asking a database for a number, what if we just take the original long URL, run it through an MD5 cryptographic hash, and chop off the first 6 or 7 characters? Voila! You've got a mathematically generated shortcode, and absolutely no shared database counter is required. Problem solved, right? Actually, scratch that, because this introduces a brand new problem. When you're hashing millions of URLs down to just 6 or 7 characters, you are mathematically guaranteed to experience hash collisions. Two entirely different URLs will inevitably generate the exact same short prefix. To fix that, you have to build out complex collision detection logic. Checking if the code exists, appending a salt, retrying the hash. It's a mess. We haven't actually eliminated the complexity here. We've just moved it around. And resolving collisions at this kind of scale, it is a total operational nightmare.
Okay, section 4, the ZooKeeper coordination solution. This is where we solve it properly. So the crucial point here is understanding what ZooKeeper actually is. Let's be clear, it's not magic. ZooKeeper is a highly reliable distributed coordination service. Its specific job, at least in our context, is to hand out unique, non-overlapping values to a group of web servers that absolutely cannot and should not trust each other's local counters. This brilliantly illustrates how it works in practice through a really elegant batch allocation process. Let's break it down. Step 1, a web server boots up and asks ZooKeeper for a batch of 1,000 IDs. Step 2, ZooKeeper uses an atomic operation to increment its shared counter. This guarantees no other server can get the specific numbers, and it assigns the server a range, say IDs 50,000 to 50,999. Step 3, the web server now happily generates IDs locally, straight from its own memory. It operates completely independently, without ever talking to the database or ZooKeeper again till it runs out of its batch. This quote right here is the massive aha moment of the entire design. We went from ask a central place for one ID every single time to ask a central place for a batch of 1,000 IDs occasionally. By batching the IDs like this, the coordination overhead drops to practically zero. We've completely removed that single point of contention. And even better, we're preventing overlapping collisions by strict structural design, rather than just crossing our fingers and relying on mathematical luck. It's a real game changer. But hold on, we can't forget the hot path. While ZooKeeper elegantly handles our occasional writes in the ID generation, our system is still getting bombarded with those 4,000 reads per second. Because these redirects are so heavily read-biased and extremely latency-sensitive, they have to be protected. We absolutely cannot hit the database for every single click. Instead, almost every popular shortcode should be served instantaneously from a massive distributed cache layer, using something like Redis or Memcached. As we wrap up, let's look at the core philosophy and the ultimate takeaway of this explainer. When you're designing systems, don't jump straight to the final overly complex architecture. It's a trap. Start naive. Build the absolute simplest working model. Then expose the structural cracks yourself by systematically adding scale, concurrency, and multiple servers into your thought experiment. You really want to let the raw requirements pull you toward the real solution. I promise you that is a vastly stronger approach to engineering than just trying to memorize some complex architecture diagram. I want to leave you with this provocative thought. If a system as conceptually simple as a URL shortener breaks this easily and requires this much coordination under the weight of internet scale, what hidden cracks are lurking in the simple systems that you rely on every single day? Scale fundamentally changes everything. Thank you so much for joining me for this explainer. Keep asking questions, keep looking for those cracks, and I'll see you next time.